ballast stabilization if we have time. I have some slides on slopes, stabilization and walls. That our partner in the UK is Greenfix. Chris, I think you're probably aboard here. I've got a couple slides on Greenfix. Greenfix has been trading since 1982, become the leading designers and suppliers of soil stabilization and erosion control systems in the UK. We work with Greenfix to develop a comprehensive range of products and systems to combat complex and diverse problems, basically associated with erosion control and soil stabilizations. They have an extensive product range, offering different solutions for house building, river restorations, coastal erosion, and of course, rail and track stabilization. Greenfix became a corporate partner of PWI in 2021, and since joining, they've mentioned that they've seen a great value in the organization and how impressed they are with the level of support, training, and knowledge of their members. So, Chris, if you want to talk, I mean, here's some of the products here.
Yeah, again, so we supply, we design and supply a range of rolled erosion control products, along with being Presto's distribution partner in the UK and Ireland. So we do a range of pre-seeded, unseeded erosion control blankets, as well as a range of self-extinguishing fire retardant blankets, which again are quite popular in certain rail scenarios, along with some anti-burrowing measures as well. Again, erosion control blankets with the anti-burrowing capability for mitigation of rabbit or badger ingress into embankments, things like that. Again, website details are there. If anybody wants any more further information on those types of products, feel free to get in touch and I can sort that out for you.
All right, thanks, Chris. Appreciate it. So let's get right into the geocells. Geocell system consists of two main attributes. The first one is the cell size. It comes in three different sizes, I guess, or diameters, about 22, 27, and 46 centimeters. Different wall heights also, ranging from 75, 100, 150, 200, and we actually make 300 millimeters, but I'll talk a little bit today about that. We've done some research in Europe, and it's pretty hard to compact 300 millimeters for railroad ballast, so we pretty much stick into 200 millimeters or less. Depending on what actual diameter you go with, there's different section lengths, anywhere from 5 to up to about 10 meters. So the ultrasonically welded seam, that's basically where all the connecting points are located, is very important to the function of a geocell. The stronger the seam strength, the better the performance of the geocell, pretty much period. So a strong seam allows for better lifetime performance. Geocells are produced using a high quality, virgin high density polyethylene for consistently strong welds at the seam, also maintaining some, basically some ductile properties, high stress crack resistance, toughness, and long-term durability. Here you can just see a typical section. It comes trifold on a pallet. Each section has a nominal width of about 2.6 meters. As I mentioned before, variable section lengths, depending on what diameter cell you go with. Basically you can see how it comes trifolded on a pallet, as I mentioned, stretches out as an accordion. It ships very efficiently. It's about 22 square meters per panel. You get about 12 meters or 12 sections on a pallet, and about 42 on a truck, so it ships very efficiently. In order for a geocell to perform uniformly, it's critical that both the factory, welded junctions, that's the internal seams, and field junctions that connect the individual parts or panels together perform at a level that is basically the same as that of the cell walls. So it's really important that any improvement in one characteristic, such as cell wall stiffness, is only valuable if a complementary improvement has been made in the other components of the system. So we've recently noticed a little bit of a trend where some providers presented performance data that appears to be equal to industry accepted standards on the surface, but then they add disclaimer languages in the fine print at the bottom of the page. So just be aware of that whoever your geocell supplier is, they shouldn't have any disclaimers on their page, and they should stand behind the data that they provide. So geocell confinement works this way. When a vertical load is applied, the active earth pressure in a loaded cell pushes back against the passive earth pressure in the adjacent cell to form a stable system. So basically each cell helps support the ones around it. The cell walls also transfer hoop stress, which is important in keeping the system intact. and creates what is known as the mattress effect. The strength of the seams around each cell, the stiffness, and the connection between panels are all important factors in determining how the system can improve site conditions. So strong seams, good resin properties, and integrated connections are critical to the performance of a geocell system. In a load support scenario, vertical deformation can only occur, with compaction or through lateral movement of the cell. So by spreading out the load in a classic approach, you can reduce the compaction of the near surface cells. And only basically with geosectality, you can ensure that there'll be no lateral shifting or rutting. Here you can see the stresses on that subgrade with an unsupported subgrade on the left and the geocell reinforcement on the right. Notice how there's complete elimination of the highest stresses at the surface with geocell reinforcement. The stresses are reduced and distributed over a wider area. Once again, that shows that mattress effect. So which leads to a significant amount of stress distribution into the subgrade. A rule of thumb, whether it's tire load, any kind of cyclical load, that when you have a point load here, a cyclical load, we're going to reduce that stress reaching the subgrade by at least 50%. And that's a rule of thumb when you're looking at a geocell design. Second attribute is the infill. Important benefit of a geocell system that even a low quality aggregate, sand, or even salvage material can be used to infill the cells. Using salvage materials, and I'll show you a couple of projects. As we go through the presentation, you can save a significant amount, not only on material, but also on the hauling costs. So we can also eliminate the fines. We don't need the fines for compaction. So if you eliminate the fines, you can get a lot of drainage to the system. So basically preventing any kind of water pore pressure buildup. So, but when I'm talking about reusing salvage materials, we try to keep the fines to, like, say 10 to 12% or less. So if you have a material that has 10 to 12% less fines, we can take a look at the gradations and see if that material is suitable to use on the system. So here you can see impressive load support. This is a 80,000 pound loaded dump truck. I took this picture years ago up in the oil patch up in Canada. This is over a CBR soils of about 1, but you can see how I talked about the loaded cells, the active and passive distribution. But you can see here, you only have 1 or 2 loaded cells or filled cells, and it's still supporting about a 16,000 pound wheel load. So it really does significantly put that stress out in a small amount of area. Nope. Sorry, my PowerPoint looks like it's trying to save. There you go. I'd like to speak a little bit on the research we've done in our geocells in our track. The first research we conducted was way back in 1990s at a place called the TTSI, which provides rail and testing for all of the Class 1 railroads here in the U.S. Has about 50 miles of track, called the Fast Tonnage Loop. We installed the geob in section 29, which was a 700-foot section. It's continuously loaded, except with new materials and idea are tested. This was a 2.5-year study conducted in the early 1990s. Mississippi mud, which is a really low strength, high moisture content soil, was brought in, has a plasticity about 3% moisture content and about 30%. So without geob, pretty much the system, the constant load and high pressure and ballast squeezed out the clays. Like I said, this was about a 2.5-year test. We applied about 185 gross tons were applied on this one. Here you can see with the geob system, the load was distributed over a larger area, which significantly reduced ballast pressure, which led to a stiffening of the sub-ballast layer. And as I said, dissipates that load reaching the subgrade. Throughout the 2.5-year test, at 185 gross tons, you can see with the impressive results. With geob tamping was required on average of every 15 million gross tons without geob to stay within the track profile of 0.5 centimeters. With geob and over about 206 million gross tons, the vertical alignment never exceeded 0.7 centimeters. About 30% of the loaded track never exceeded 0.5 centimeters during the 2.5-year test. So at one point, even during the test, they brought in 100,000 gallons of water. They dumped it over to induce failure, but no really effect was measured. So the test section is actually still in place today, about 30 some years later, and it's operating just fine. So based on that testing and a lot of information from our Class 1 railroads here in the US and also some network rail in the UK, we wanted to do a testing program basically with some different types of technology. we did a testing program at the University of Kansas. In addition to University of Kansas Research, Oregon State University performed finite element analysis. Each test was instrumented with smart rocks. You can see they're shown on the lower portion here of the screen. Each smart rock included a motion vibration sensor that could record rotation, translation, and orientation. So earth pressure cells were also used to measure the vertical stresses and the displacements at the interface between the ballast and the subgrade. Once again, the research was conducted University of Kansas. Dr. Yi Han, who has been researching geocells for over 20 years. Ben Lashinsky from Oregon State did his PhD research and thesis on geocells, also conducted the finite element analysis. And Professor Hai Hong from Penn State University here in the States provided the smart rock technology. So the testing consisted of basically a 37 kip wheel load, 75 mile per hour speeds, and 136 pound rail. We varied the subgrade from 0.5 to 5%. We did a total of 8 tests, 3 control tests, and 5 supported tests with the minimum passes of 1,000 passes. So to evaluate the movement under those cyclical loads, as I mentioned, we added the smart rocks to the ballast layer. So we added them halfway between the bottom of the tie and the panels, and also inside of the geocell panels. So, the smart rock, measures that particle transition, acceleration, and velocity in all the directions. So we're actually looking to confirm, how stabilization, geocell stabilization controls ballast movement, not only inside of the cells, but also between the bottom of the tie and the top of the cell. For this test, here you can see inside of the geocells. This ballast was 300 millimeters, so 12 inches. So we actually placed these smart rocks halfway between the bottom of the tie and the top of the geocell layer. So about 150 millimeters below and 150 millimeters above the top of the geopanel. And here you can just see how the smart rocks measure movement of the ballast rock. This is both rotationally. So here you can see this is rotational. That's measuring the rotation. You can see on the graph how it's measuring that. And we also measured the movement in all directions. So here you can see it's measuring that horizontal and vertical movement of that particle, that ballast particle. So this slide shows the results. The 2 graphs on the left show where the smart rocks are placed in the middle of the ballast layer between the bottom of the tie and the geopanel. This is probably the most important one. You can see the control section on the left. So this is 150 millimeters below the tie and above the geocell. You can see that with the control section, you get a lot of movement of that ballast particle. But with geocells, since we reduce the amount of stress reaching the ballast, we really control the amount of movement, not only inside of the geocell here, as you can see, but also between the top of the geocell and the ballast. So it's very interesting that, the testing showed that we stabilize not only the inside of the cells, but also in that ballast layer. That's one of the things that the class ones here in Network Rail were saying, is that using geocells in the ballast layer significantly reduced the amount of tapping that was going on. So they wanted some testing basically to verify that. This slide shows the angular acceleration, which is how fast the particle moves. Once I said back and forth due to cyclical loadings. Just like in the previous slide, you can see how the control movements in the cell and below the tie. You can see the movement, with control. You got a significant amount of movement in that ballast layer. Stabilized with geocells, you can see how we significantly reduce that movement, that particle movement, that ballast particle movement. And then once again, inside the geocell, you can see at the control, which is less than 300 millimeters below, and you can see that stabilized with the geocell. So the test results clearly show that, geocell stabilization, significantly reduces particle acceleration velocity, not only in the cells, but more importantly, below the tie. So, the results show that stabilization can effectively minimize that ballast movement by providing a lateral confinement, so that, you don't get some vertical compression, breakage of the ballast. The traditional lateral spreading is minimized, and performance can be significantly improved. So by controlling ballast movement and rotation, this will lead to decreased ballast tamping and reduced maintenance, which directly leads to cost savings. We also did some finite element analysis to confirm the reinforcing benefits of geosol stabilization. Finite element analysis is used to solve, pretty complex problems by looking at both unstabilized control section in the left and a stabilized section in the right. They can show how they change under cyclical loads. The analysis used that differential equation to determine the results here. The picture is an example of the output showing vertical sediments at the subgrade as CBR of about 0.5. So the use of geo confinement was effective in redistributing the vertical stresses in the subgrade, resulting in larger areas of subgrade mobilization shear strength and reduction of plastic deformation. So geocell reinforcement decreased the pressure at the ballast in the subgrade interface by at least 50%. Geocell reinforcement also increased the load-bearing area of the subgrade and resulted in decreased interface pressures. The decreased pressure in the subgrade results in lower settlements. If you're interested, we have research summaries from the University of Kansas, from Dr. Yi Han, including the smart rock testing, and from Oregon State, Dr. Ben Lashinsky, that does the finite element analysis. So it basically provides basically a summary of the description of the testing and the impressive results. So I guess now we're going to talk a little bit about some rail applications. Geosols can be used under track for all different types, whether straight line track, special track work, bridge approaches where we're trying to eliminate, get that bump at the end of the bridge, grade crossings, any type of frogs, turnouts, any kind of high stress areas. Geosols can be used to eliminate any kind of settlements. This is a project consisting of miles of new track from Network Rail. This was on the northern hub on the Bolton Exton line around 17 mile. Parts of the track that were enhanced on the northern hub were located on soft grounds, very low shear strengths. As a result, a standard required depth of track can be as high as 1 meter. As you can imagine, that's very expensive to construct. So Network Rail, the investigation team was tasked with finding alternative design solutions to reduce the depth of the construction. So using Network Rail in-house modeling capabilities and the Presto design method, the use of geosols was proposed as a viable alternative for the track bed solution. So numerical modeling was also used to qualify the allowable reduction of track bed depth if geosols were to be installed in the track bed. Similar as a typical solution. The model was further used to iterate different geocell layer thicknesses and compared the performance indicators with the baseline values for the standard track bed design. The iterations showed that using a track bed design that consists of 250 millimeters of ballast, 150 millimeter deep geocells filled with granular fill, and a 50 millimeter sand layer provided a similar performance to a standard design solution and saved at least 80 millimeters of depth. So it's important to point out that the reduction in the required track bed construction, about 40%, in the granular layer, due to the use of the geocells, saved about a reduction in cost about 22%. Here you can see just a couple slides. Non-woven geotextile separation was placed over the 50 millimeter sand layer. 150 millimeter deep geocell panels were placed and filled with the crushed aggregate. The contractor just spread out the infill. You can see is spreading it out and in place the ballast layer. After the successful installation on that Bolton line and opening the track to traffic in early 2017, the geometry was monitored on a monthly basis. So this slide shows the track quality standard deviation for 1/8 of a mile for the worst top 35 meters and the mean top 70 meters. From the figure, it can be noted that the track quality is significantly improved to an excellent condition for both the top 35 and the mean 70 meters. So to understand the effect due to geocells, the track quality and rate of deterioration after the installation can be compared with track quality deterioration after the most renewal before the installation of the geocells in 2020. So here you can see, here's our geocell installation back in 17, going through 2000 with a very, very small uptick in any kind of settlements. And before with their other, you can see the significant amounts of settlements they're getting without any kind of geocell reinforcement. This was a comparison between the track quality after the last major renewal in 2002 and after the installation of the geocells in 2017. You can see that from the table that after the installation of geocells in 2017, the track quality and deteriorations have improved significantly. Deterioration after renewal in 2002 ranged from 0.7 to 0.9 millimeters per year. The installation for the geocells has deterioration values from 0.1 to 0.15 millimeters per year, which is a pretty significant improvement in stabilization. So based on that successful geocell installation, Network Rail decided to develop a guide with a goal to provide a summary of the benefits from the research and testing, design recommendation, and the best practice for geocell installations. So in August 2020, Network Rail issued the use of geocells in UK railway trackbed techno guide. The guide was supported with a review of some of Presto's lab research testing, the University of Kansas and Oregon State, existing design methods, case studies from successful installations and installation methods. Prior to approval of the guide was peer-reviewed by 6 recognized professionals with rail experience. Ben Lachinsky was part of that peer review. The guide was a reference for the Network Rail trackbed standard, issue 2, issued in September of 2020. So that basically contains the detailed design information in the guidelines for geocell. So the standard provides the guidelines for engineers to include geocells in their designs. Approximately 3 miles north of Peterborough Railway Station, another major works taking place. This is Warrington Junction. The aim of this project is to increase the capacity for passenger trains on the East Coast line as this part of a $1.2 billion upgrade. The scheme is referred to as the Warrington Dive Under or Warrington Grade Separation. Involved building a new 2-track rail line with tunnels under the existing line. The new line opened in 2021 and moved constraints to the train timetable caused by the slower freight trains on the Great Northern Road. That currently has crossover high-speed East Coast line. The project consisted of about 1 miles of new line with geocells to improve under track thickness. So basically in areas with poor soil, poor drainage, and to eliminate that deep excavations. And this area had a lot of poor soils. So we went with a enhanced woven geotextile. That's a geotextile that provides strengths, about 70 kilonewtons per meter of strength. It also allows a lot of drainage and filtration. It doesn't allow any of the fines to come up. We also included a 200 millimeter panel of geocells filled with local sands. One of the advantages of using geocells, you can see is you can use that granular material as we discussed before, even coarse sands. You can see on this installation, they're using a coarse sand to infill the geo panels. They're very flexible. You can use any kind of low quality fill, or like I said, even recycled ballast. And as I mentioned before, keep that fine content to less than about 10 to 12%. And here you can see the contractor wanted a very precise installation. So they use stretcher frames to keep the panels open as they filled them up. As they went along and filled them up, you basically just pull these stretcher frames and go on to the next panel. This is a project, very interesting project. Was done down in South America. I wanted to show this was for mainline track, about 10 miles of mainline track. It's on a heavy coal line. Subgrades ranging from about 1 to 3% CBR. It had in some areas had a decent subgrade, but the main problem with this one is the ballast become fouled and required ongoing maintenance. So this was a project, as I mentioned before, how we can use salvage ballast. You can see how the salvage ballast was stripped from the site. The original ballast here stockpiled and then used to fill in the geocell panels. So as stated there earlier, this project was about 10 miles track with 150 millimeter geocell. So they say it bring in about 12,500 cubic materials or meters of material. So you can imagine how the cost savings provided to the owner by the use of geocells for this project. And not only the cost savings from the infill and hauling costs, but also, becoming very important today is the reduction in carbon emissions due to not only the transfer of the material, but also to the production of that ballast. And here you can just see the salvage ballast being compacted in place, the enhanced woven geotextile here, and the 250 millimeter ballast layer, sleepers, and the rail. This is a project we did up in Northern Canada. If anyone's been to Northern Canada, it's basically muskeg. extremely poor subgrade CBRs, typically, 1.5 CBR or less. Once again, the railroad's having to spend a significant amount of time here in maintaining this 1.5 mile long section. They're getting a lot of settlement. You can see a lot of fouling of the ballast. Here you can see a lot of ballast contamination. You can see how bad the pumping is on the next slide. I'll show you here, but you can see how much the foul ballast is. Led to a lot of maintenance on this site, and this was a very remote site, so it costs a lot of money to basically maintain this 1 mile long section. Here's a video. You can see after every train goes by, you can see how the depression in that track. It's a significant amount of pumping and depression. They're measuring track depressions over a couple inches, so a significant amount of depression in certain areas. Since the subgrade was so poor on this one, this had anywhere from 0.5 CBR in some areas to 1. We actually recommended factory sewing of that enhanced woven geotextile. We typically use something called ASHTO M288, which is our highway standard for overlaps of CBRs or fabrics for CBRs. Usually, if you have a CBR of less than 1, we typically recommend looking at factory sewing of the geotextiles. If it's longer, each one is about 15 feet. So this track was about 30 feet long. So we actually, you can see here, factory sold that geotextile. It provides a stronger, because you don't have the overlaps. And if anyone's tried to install a geotextile in the field with overlaps, if it's windy, you can just imagine this one would have required a 1 meter overlap here. So we saved a significant amount of money in the waste of geotextile that was required for the overlaps. The factory saving does cost a lot, but it's significantly less expensive than wasting a 1 meter overlap, and a lot easier to install in the field. So you don't have that concern with winds and trying to keep that overlap in place. Here you can see the insulation of the geob. Like I said, this is a very remote area. They used actually waste mining rock here for the geocell installation here. You can see it ranged from about a 1/2 inch up to 1.5 inches, 2 inches for the gradation. You can just see the finished installation, final ballast placement. You can actually see how they extended the geocells outside of the ballast about 3 feet, 1 meter, and they came back afterwards and just basically respread the ballast layer. You can see that doing that in the background here. And the final ballast placement. This is a project in St. James, Louisiana, about an hour or so west of New Orleans. This is a food manufacturer. We had to actually construct a track that crossed a sugarcane field, about 1 mile of track. The subgrade was very, very poor, very, very wet, high groundwaters. It's in the swamps of Louisiana, so you got a lot of groundwater. You can see how basically the tracks here. This track was constructed with geocells. Also, this one, they wanted to add that main track right down the center. So you can just imagine all that water is getting stuck between these two tracks. So we did a cross section for them. Once again, we factory sewed the geotextile in the factory, and we put down about 8 to 10 inches of a bigger rock, just to get it up to grade to keep it out of the water, more or less. And you can see here how they are filling the geocell. And once they get done filling the geocell, what we talk about is, we call it a burrito wrap. So what you want to make sure you do on low subgrade CBRs is, if you have a planar geotextile, you want to make sure you wrap the sides here, because what will happen over time if you don't wrap the sides and provide that geocell or that burrito wrap, what's going to happen is, over time with the cyclical loads, you're just going to squeeze that layer underneath the geocells, and it's going to deform. Your track's going to start to settle. So make sure that you wrap the geotextile over the top of the geocell, and then basically put in your ballast layer. We do a lot of high stress areas, grade crossing, diamonds, intersections, things like that. I got just a really interesting little project. This is a high stress area. This was a crossing. This is down in Texas. This is one of the class 1s here in the US. This crossing, the existed of standard concrete panels, wood ties. The crossing was located adjacent to a concrete plant. So very heavy trucks are damaging the crossing. So the system prematurely failed due to the excessive braking and acceleration, being transferred to the crossing in the subgrade. Those concrete trucks were stopping here every time at this crossing, just due to safety concerns, to check both ways to make sure the track. So the concrete panels didn't hold their position despite they actually leg tied the ties and tack welded to each other. So several panels failed completely and had to be replaced. So we designed the cross section using 6-inch geocell and once again enhanced woven geotextile. We extended the geocells outside of the crossing at least 2 panels in length, so about 13, 14 meters. This project was also interesting because this was the first composite or plastic grade crossing in the United States. You can see here the composite grade crossing. The enhanced woven geotextiles, they're butting it up to another layer of geocells that was under the crossing. And I said this is the first one in the States. Here you can see the first train, through the grade crossing prior to even finishing the installation. This project was completed in 2017. And since then, so going on 6 years, there's been zero settlement or deformation of the roadway or the track structure due to the loading and the braking. So no maintenance in the last 5+ years. Another good thing about geocell crossings and repairs, especially when you're looking at comparing it to asphalt, most of the crossings that we do, especially the smaller ones, are done overnight to reduce downtime in the trains. Usually it can be finished in about 4 to 6 hours, depending on the size. The crossings are typically taken down around midnight on a Saturday night and back in operation Sunday morning. So unlike asphalt crossings where you need the plant to be open, geocell crossings are very flexible. So you can schedule a downtime, anytime you want. This is a lot of times these crossings are actually done by the railroad personnel. So here you can see this one, and so once again, a standard crossing. This was about 20 panels of GeoWeb, so about 4,000 square meters. Once again, you can see an enhanced woven geotextile going, the geocell being placed in with a sandy agate that the railroad uses for some of their installations under track. And you can see the ties and rail being reinstalled. Like I said, it's very important. Remember that, they're very fast to install. 6 hours for pretty much standard crossings, and they don't have to worry about the plants being open for asphalt. So it goes in very fast, very effective system for installation. Another really important area that we try to help out is on bridge abutments. If you do a lot of research on bridge abutments, everybody talks about that bump at the end of the bridge. We're trying to eliminate that, due to any type of, when you build a new bridge especially, it's almost impossible to compact it completely. So you're going to have some consolidation settlement over time at the bridge abutments. So using a geocell, since we can reduce the stress so much reaching a subgrade, we can't eliminate the consolidation settlement, but we can decrease it. So we can really try to lessen that bump at the end of the bridge. So, a lot of the class ones in the US, and we've been using it all over the world, actually will put the geocells at the end of their bridge abutments, whether that's a new track construction or an existing bridge that's having a lot of settlement issues, to eliminate that bump at the end of the bridge. We do a couple different methods. A lot of times we'll put one geocell layer, and then we extend out 2 panels in length. For say bridge abutments that aren't that high, maybe up to about 20 feet. If we go over 20 feet of really high bridge abutments, what we'll do is we'll actually put in 2 layers of geocells at the end of the bridge. So we'll stack these 2 high for 1 panel length, and then we go to just 1 layer of geocell extending out. So 2 layers, 1 panel length, and then going to 1 panel height and 1 panel length out. That really does dissipate that stress at the end of the bridge and get rid of that bump at the end of the bridge. So in summary, geocells are very efficient for road projects. They provide stable and longer lasting ballast, which will reduce maintenance and repairs. So the ability to use a low quality aggregates, coarse sand, or even salvage ballast, can save a significant amount of money. But like I said, it's not only the money, it's the carbon savings also. So the ability to reduce the stress on the subgrade will control that differential settlement and will definitely reduce the amount of research. So we have the testing to back it up, not only in the US, but also in the UK. So controlling movements in the rotation will significantly reduce ballast attrition tamping, and your maintenance costs. So make sure if you're looking at a geocell project to you work with a geocell manufacturer, provide a complete set of calculations, not only for their geocell, but also what type of geotextile is going to be required underneath the geocell, depending on the type of conditions of the subballast. And you want to make sure that the geocell layer is as high in the ballast layer as possible, because that provides the most benefit to stress distribution. The deeper you put it into the subballast, it provides less effect. So you want to make sure it's really high up into the ballast layer or subballast layer. So I got some time to talk a little bit about slope protections and maybe some earth retention. Just like in rail, it's very flexible for slopes along rails. We can fill it with aggregate. If you want a hard solution, we can vegetate it, fill it with topsoil. Also, a lot of areas we do concrete, especially on culverts that cross rails, we'll do concrete slope stabilization, where no maintenance is required. On this project, this was about 20,000 square meters. This was on two sides of an embankment. They wanted it for erosion control. You can see we always deliver the material for the top. Here you can see they used anchors on this one. This was about a 2-to-1 slope. So we had rebars with a stake clip on top with a Hilti hammer driving the anchor into place. But once again, you can see always installing the material from the top. Just a close-up picture showing the panels and extended under the bridge abutments to the other side. Like I said, this is about 20,000 square meters. They wanted to have a hard, I guess, sort of a hard armor solution because they didn't want animals to be anywhere near the slope and the bridge abutment. Here you can see a picture of the finished slope a couple of years later. You can see sand infill. You want to make sure that you size the infill when it's aggregate based on the amount of water that's going to be on that slope. So you want to make sure that you have research and testing that backs up what size rock you put in there based on how much rain you're going to see coming over the slope. This project for the new siding, this was another project done in Texas. This installation about 42,000 square meters. They used 100 millimeter deep panels. With this, once again, this was a crushed aggregate. It doesn't get a lot of rain. This is like in the desert on the eastern side of Texas. But when it gets it, it's in short and large bursts. So the railroads wanted the geocells to prevent erosion on these sidings to eliminate the need for maintenance. So this was a pretty big job. They used 30 millimeter crushed infill on this project. You can see here, once again, this is where they're just basically tying the geotextile and the geocell into the top for crest anchorage. Here you can see the panels prior to infill placement. Large riprap was provided on the bottom, basically because they got so much overland flow and it runs to the culvert. So here you can see the large culvert pipe under the rail with the riprap protection. So like I said, it doesn't receive a lot of rain, but it does. It receives a lot. That's why we had such big riprap that we had to size along this culvert pipe. So when the water comes through, it's about halfway full. So we wanted to make sure that we had enough big riprap. So we sized that riprap for all that overland flow. So basically, you want to make sure that you provide a full set of calculations. For your slope protection, you want to make sure that you're sizing for the right anchors. Whether that's rebar anchors driven into the slope, plastic anchors driven to the slope. A lot of times we'll use tenons, and you support the geocell from the top of the slope with a pipe deadman, basically like hanging a set of drapes for the pipe deadman. You want to make sure that you size the deadman correctly, based on site-specific conditions. So you want to make sure that you have the number of tenons. Don't rely on existing tables. There's no job is standard projects. You want to make sure that every job you get a certified or an evaluation from the geocell manufacturer based on your specific project, and don't use standard tables because it's very hard to rely on standard tables. So in summary, the geocell slope protection is great flexibility. You can do a lot of infills, you can do aggregates, topsoil, or even concrete. We've installed slopes up to 70 degrees if the slope is globally stable. So it's a very good system and will definitely stabilize your slopes. Gravity walls or reinforced walls. Gravity walls typically up to about 3.5 meters. It all depends on the subgrade surcharge above the wall. MSE walls, anything typically over 3 meters, or if it has a lot of surcharge loadings. The panels, here you can see the geocell panels are very flexible. They can be cut in the field. Here you can see a standard geocell MSE wall, reinforced wall. You got the geogrid tiebacks. Here's just a typical reinforced wall. This was actually reinforced. We did it on both sides of the bridge abutment coming out. We put geocells underneath the track here, but also for the wall for stabilization because they had limited right of way, so they couldn't actually extend their slope down. So we built the geocell wall, and you can just see train coming through it. Rule of thumb for this slope, about 2 to 1. You want to keep it 2 to 1 or less. Don't ever go over 2 to 1. This is a project, another wall that we did that was in a railroad right away. Was used to prevent basically global failure and stabilize the line. Here you can see this one was installed in somewhat here in the States. This was installed September. So this is a cold area. This is in Ohio, so it does get snow. So they hydroseeded this wall, and this is what this wall looked like back. This was early summer, so June, July of the next year. You can see complete vegetation. So a very nice looking wall. You don't even see it. So good aesthetics. We offer a program called Geob MSE. It's a free software. It's used to design any type of gravity or MSE wall. You really just enter the parameters. It was created by Doug Lashinsky, who's pretty much a world-renowned wall expert. It can, like I said, can do gravity and reinforced walls. You can run it in design and analysis mode. Like I said, the good thing about this, it's a free software. It'll print out standard cross section. It also gives you a nice summary of your design. It'll give you your geogrid tiebacks. We have over 30, or actually 20 types of geogrids that you could insert into your program to do the design. Basically, you're selecting here what type of wall, whether the depth, different sizes. So a 30V is our mid-size cell. That's going to be about 10.5 nominal diameter. So you can actually, it's a lot of different parameters that you can select. And like I said, the software is free. We'll actually do the design for you, or we'll help you with it. So quick summary on earth retention. You can be used for gravity and reinforced walls. They're very flexible. The front fascia can be filled with topsoil, aggregate or concrete for non-vegetative fascias. So like I said, make sure the wall design is accomplished using the proper computer software, based on the geocell parameters specifically. So with that, I'm pretty close. So I guess thank you for attending. We appreciate you taking the time out with your busy schedules. My contact information is here. If there are any questions that come up, we can address them not only today, but my email is also there. And Chris Metcalf from GreenFX is also on the line. He's available to answer questions locally and provide local support. Not only pricing and installation support, but also technical support. Chris has an extensive background in geosynthetics, not only geocells, but also in geogrids and geosynthetics. So with that, if there's any questions, be more than happy to answer them.
Well, Bryan, thank you very much for that. Very comprehensive review of the GeoWeb system. It's good to go into the science behind, excuse me, what it's all about, and to look at some of the applications. And clearly there are a lot of applications which you apply this to. So there are quite a number of questions on the chat, although I've just managed to lose them from my screen. So just bear with me a second. Perhaps if I could go first to Sean Merrifield. Sean, you asked the question, and being as it's been quite a while since I've heard your dulcet tones, would you mind unmuting yourself and asking your question of Bryan? That's probably better coming from you. Sean, are you there?
Yeah, sorry, sure. Yeah, I was just
sorry, didn't mean to spring that on you.
Pose then, I'm just trying to dig up my question. Actually, I did ask it.
I can do it if you need me to, but
no, that's right. I just found it now. So yeah, sorry. So Bryan, some of the earlier geocell products that we used on the railway were typically kind of fabric-based ones, which when you kind of stretch them out, you had to kind of stake them in every other pocket. and it was quite time consuming and labor intensive. I see your product that you're promoting today is kind of HDPE pockets, which seem to be much more robust. And the question was, do you need to stake out these GSLs in the same fashion? But then I think later in the presentation, you mentioned about stretcher lines, and I just wonder how frequent they need to be installed. And we're looking on a flat surface under a railway, as opposed to the cutting slopes where you've already mentioned about the ground anchors.
Yeah, I think you're referring to the non-woven geotextile geocells. We invented the geocell technology back in the late 70s for the Army Corps of Engineers here in the States, and it was always based on a HDP or plastic geocell. So I always tell people it's like hanging drywall. You want to make sure that the first couple panels are installed sort of square. So it might take a little bit more on the first 1 or 2 panels, and we'd recommend staking or temporary staking the corners and the middle points. So you have, like, let's say 6 stakes per panel. But once you get that all nice and square, and you can remove those temporary stakes, you infill it, remove the temporary stakes, and from there the stress when you pull out the panels, the weight of those panels that are installed and infilled, you don't need a lot of stakes. Right? Network rail and that one I showed you is the temporary stretcher frames or the stretcher bars to keep the panels open. You don't specifically need those. It does help with a straight line installation. I'll be honest, a lot of contractors will put in temporary rebar every, say, 10 panels or so, or just use the bottom of their shovel as they fill it in to keep it open. So it's not required. It does speed up installation though, but they're not permanent. They're just temporary. So as you're filling it, you just remove that temporary stake and go to the next panel.
That's brilliant, thank you. I was very greedy and I asked 2 questions, so if you're happy, Stuart, to go for the second one. On the railway construction, our kind of construction widths are typically around about 3.9 meters. And at the beginning of your presentation, I think you said that you had a 2.6 meter width panel as a standard off the shelf kind of thing. Do you have panels as well? Because what we're very keen these days is to avoid site cutting and waste. And if you had a half panel and a 4 panel, then that gives us the 3.9 meters to lay down quite quickly. And the other question related to that is, if you do have kind of encroachments into your dig, like foundations or other kind of services you need to cut around, how easy is it to cut these HDPE pockets on site, and what would you tend to use as your go-to tool, really?
So as far as the panel widths and the panel lengths, it depends on your specific installation. So if you have like a 3.9 or I think you said 3.9, if we install them parallel to the track, we can overstretch or understretch the geo panel. So that 2.6 is more of a nominal. But if it's like a 3.9, we have different section lengths. So in those applications, to basically eliminate waste, what we do is we install it perpendicular to the track. So we have multiple section lengths. So we always have a section length where we can accommodate anywhere from, say 2 meters up to, 10 meters. So it's very flexible. So we'll help you decide which way it should be installed to basically eliminate waste.
Perfect.
Thank you, Sean, and thank you, Brian.
Mhm.
Next question. Well, in fact, there are 3 questions from Santanu, of which, if you don't mind, I'm going to ask 2 of them. First one, the graph with rail deflection versus GMT. There was a section where rail deflection increases and then improves. Was there a particular reason for this? Was it that there was an intervention made somehow?
I think they're talking about the Warrington route, where we showed they had a bunch of improvements. That track was significant problem area as far as maintenance and repairs since 2000. They improved that track, many times through the years, but it always requires some type of tamping. As we get to that slide, I think this is the one they're talking about. Maybe I think it might be this one here.
No, the earlier one. There was one before this one where.
On the research, maybe?
Yes, probably. No, not this one. Even before. It was just at the beginning. Well,
Oh, this
yeah,
one.
this one. So you
Oh, yeah,
mentioned
that,
there was some water also poured in the site, and I believe the deterioration is due to that. But next when we increase the GMTs, it kind of improves. This is my question.
yeah.
So
Trying to
was
get to
there
that one.
any reason? So if you see between 40 and 60, it's
Yep.
going worse, isn't it? And then it improves again.
Yeah, so what they did is they put some water on it.
Yeah.
Yeah, that's what so they kept adding water and letting it dry out, adding water, letting it dry out. This was like I said, this was back in the 1990s. We did this testing. This one included just a non-woven geotextile over a subgrade CBR of about 2.5. So today we would not use a non-woven geotextile, especially over, high plastic, a lot of fines in it, because what happens with the non-woven geotextiles is since it's 3D in nature, they clog. So if you have a lot of fines, that those clay fines can get up into that non-woven geotextile and clog it, since it's 3D. So that's why we go with those enhanced woven geotextiles, where it's a planar, it's not a 3D. So what happens with those geotextiles that are planar, the enhanced wovens, you allow water to flow freely back and forth, but it keeps the fines from following the ballast.
Okay.
GreenFix offers a bunch of different enhanced woven geotextiles,
Mhm.
but they're a very good product, and especially you should really look at those because with the costs of everything increasing, the enhanced wovens are getting pretty close to what the like a heavyweight non-woven geotextile is. So it should be looked at, because GreenFix has a couple, ranging in 40 kilonewtons per meter, up to over 100 kilonewtons per meter. So you're getting, versus a non-woven geotextile where you're just getting separation. With the enhanced wovens, you're getting reinforcement, separation, and filtration. So
Okay.
highly recommend looking into those geotextiles when you're doing any type of rail design, even when it doesn't include a geocell.
Okay.
Thank you, Brian, and thank you, Santanu. Actually, I'm going to ask you a third question because it's quite different from the first one. Because I did note through your presentation, Brian, you did highlight a lot of environmental gains from what the product could bring. But Santanu's question was the opposite. Is there any environmental disbenefits in terms of materials, etc., that we might see through using this product?
No, a lot of the PFAS contamination everybody's worried about these days with some other products. We don't add any type of fillers or any type of unlike some products that are extruded they add materials to allow it to be extruded.
Right.
Like some geogrids will add different products to allow the the extrusion of the geogrids. We're basically a 3D system. We had 100% HDP, a little bit of carbon black, so we don't have any of those fillers. We don't have, so there's not a PFAS problem whatsoever. We have research and testing on that that we can provide. I know that's becoming a pretty big deal all around the world. So, like I said, since we're 100% HDP, we're not going to have any problems with any environmental concerns.
Right. Thanks.
Great, thank you. Question from Anantha. It's asking, are there any speed limits to using the product? I presume that's line speed limits.
Not that I'm aware of. We've done on a lot of high speed loops all around the world. I mean, one of the first installations we did in rail was actually in British Rail. That was up to about 80 miles per hour. That's still in service. We've done high speed rail all over the world. Our design method is based on speed, so it takes speed into consideration. Basically speed is a little more stress on the subgrade, so it might require a little more sub ballast. But yeah, that's all taken into account when we do the designs. Not only speed, but we look at the tie space for sleeper spacing, sleeper type, whether it's concrete, steel, or wood. We look at the dimensions of the sleeper. So there's probably 10 or 12 different things we look at when we do a rail design. So make sure, speed is very important, but so is you're looking at all the different parameters for rail design.
Great, thank you. I'm going to nip in between some questions here because I'm very conscious that we've reached the end of the hour, but if I can get a couple more in. Paul Inslee asked, one of his questions was, have you used 2 layers of geocell in poor track locations, i.e. sub and superstructure?
Yes, yes, we have. to be honest with you, though, with the development of these new enhanced woven geotextiles, you know, geocells are more expensive than geogrids or geotextiles. So what we've come to look at is if we put down, like I showed you on that project in New Orleans, we could have put down 2 layers of geocells, but it wouldn't have been cost competitive. So what we do is we put that high strength enhanced woven geotextile on with a sub ballast underneath the geocell. So we might have, say, a 150, a 200, or 300 millimeter ballast, then the geocell, then the ballast. So it's a lot more cost effective, and it gives you a very good installation. So the answer is yes. You can do 2 layers of geocells, especially at the end of bridge abutments. That's important. But as far as straight line or mainline track, it's not cost effective. It provides just as good of insulation go with an enhanced woven geotextile in a Brio wrap geocell.
Okay, thank you. I'm going to ask 2 final questions. Firstly, Suzanne obviously works on London Underground, and she says we suffer from shallow depth ballast. Is there a minimum ballast depth that you have to have above the geocell?
No, we want some protection, so we say a minimum of 50 millimeters to protect the top of the cells. But you know, basically our limitations for under rail is usually determined by the tamping. So most rails around the world, I mean, I know it's a different installation, but for straight line track, we're typically about 200 millimeters below. But we have done tunnels before where we just had 50 to 75 millimeters of ballast over the top of the geoweb.
Okay, thank you, Brian. So I think the last question is about the longevity of the geocell system. A number of people have asked, how long does it last?
Well, it's made of 100% HDPE, so it's plastic, and we add black to it, a couple percent carbon black, but that's only preventing is UV damage. So if you, and we've done research and testing, and other manufacturers have also in laboratories, is that if you subject a geocell with carbon black to direct sunlight 24 hours a day, 365, the carbon black lasts for 140 years. So that's even before the plastic starts to degrade. So if it's buried in the ground, it's going to pretty much last forever. If you ever done any landfill work and you go out and you dig a hole into the landfill and you pull up everything that's plastic, and when I used to do landfill work when I was a consultant, all we found is McDonald's toys from the kids' meals. So, and they were perfect from 15 years ago. So, yeah, geocell, I wouldn't worry about the lifetime of a geocell, especially if it's designed correctly with the right panel connectors. That's the biggest thing. So you don't have panel separation. So
I guess if we're not worried about it's degrading, I wonder when we come to renew the track again, if we have to, are there any issues with removing?
Nope. You basically just rip it up with a bucket on an excavator and redo the ballast. If you have to do some, like install a pipe crossing the track, you know, it's easy to cut the geocell with a PVC pipe saw, and you can just patch in a panel. So yeah, it's very, very flexible for that.
Right.
And if anybody has any questions we didn't answer, I'm sure, Stuart, they can get a hold of you and myself or Chris from GreenFix.
Well,
be more than happy to answer.
No, you great. You've just got me to where I needed to go. So firstly, thank you very much, Brian. That's a fascinating presentation. I think very informative, and you can see from the comments coming through that it certainly appeals to a number of people who are looking for the sort of stuff that you're offering here. In terms of future questions, what everybody will find is that we will have a LinkedIn page associated with the PWI. So Brian, if you're happy, if people want to pose any questions, maybe that some I didn't get to here, my apologies, or any others, if you're happy to carry on that conversation via that medium, then that's an opportunity so people can continue to ask. So hopefully that's okay, Brian.
Sorry, I muted myself. So you said that's a LinkedIn page?
Yes, so we have a LinkedIn page for each of the Lunch and Learn sessions. So if anybody wants to go on and ask anything, obviously you can see it, they can see it. We can facilitate that. So yeah, a good way to carry on the conversation and perhaps get some answers to questions that either didn't get posed or couldn't get posed because of time.
Yeah, absolutely. And like I said, the main purpose of this presentation is to enhance geocells in rail markets. So absolutely. Stuart, could you just send me the link to it so I
Yeah.
can join the page?
Yeah, absolutely. I can do that.
Yep, not a problem.
Brilliant. Okay, well, just in closing to say we've got a couple more sessions coming up, firstly in 2 weeks, then in 4 weeks. First one is track condition monitoring using noise and vibration analysis. So certainly for all the maintenance guys out there. And following that, a presentation by the S&C Alliance work, lots of things around S&C Alliance. And I guess just before Rail Live, which a number of you may well be going to. So again, perhaps that's an opportune moment. So finally, thank you, Bryan. Thank you, Greenfix, for a very interesting presentation. And I hope you all enjoyed your lunch.
Yep, thank you, Stuart.
Thank you, everybody, and goodbye.
Thank you. Cheers.
Goodbye, everybody.
Thank you.
Thanks very much. Cheers.